Hello, also we are back with our Ranchoddas webcast series this month. I hope this was not a very long time since we actually came online. So yeah, so today we have a presentation on shellcode for ARMS. Your pills don't work on me, x87, 86 by Svetlana. So basically, who we are, actually, we started as amateur hackers in 2007. Basically, we started from one of the social media site, Orkut. There we had a community of around 2,000 some members. In 2004, we actually got into forum, and we started our own forum where we started posting our various articles which we shared on Orkut community as well. Yeah, so basically, in current state, we are a family of 4,000 plus users, and we already posted around 8,000 plus posts. 40 plus bug bounty submissions to vendor like Google, Facebook, Yahoo, and some others as well. Some of our members are also into Chrome, IE, and other browser fuzzing, so we have some CVs. We also release some of the unknown zero-day vulnerabilities such as ASLR bypass method even before it is getting into some conferences and it was public to others. We have a lot of research papers based on biometric, lockpicking, cable TV network, and data cards, which is generally not much of a fame. Yeah. So this webcast will be all about shell codes for ARMS. Basically, nowadays we know that mobile phones are very much based on ARM processors. So yeah, that will be the key. We have the author Svetlana, who is a PhD student and also worked as an intern in Microsoft and other with us. Yeah. We would like to thank our sponsors for helping us to get these sessions up and live. We would like to thank NetSparker, HITB Conference, and Workspace. I would also like to thank our media sponsor, the Hacker News, for spreading the word. And mainly our G4H team, who actually behind the scene working hard for getting this live. Would like to thank Dheeraj, Himanshu, Ajay Singh Negi, and Chaitu, and all other RWS team basically. Yeah. So Svetlana, you can start. Yeah.
Okay, so first of all, I'd like to thank all of you guys for inviting me for such a great event. So it's like, sounds very cool. So secondly, so hi everybody. So I'm going to talk today about shellcode detection actually. I've started this work 4 years ago, and for now, so first of all, the work was based on x86 shellcodes, which were written for x86. For now, me and my student Ivan Petrov, with whom I did this work actually, we focused on shellcodes for ARM processors. So let's start probably. I'm sorry, I have troubles with full screen mode for my presentation, but anyway, let's do it like that. So actually, here is our credentials for me and Ivan. First of all, I'd like to briefly describe why I think it's still important. For now, the number of ARM-based devices growing increasingly, and for now, it's in times bigger than amount of devices for like x86 platform. It's all about our cell phones. It's all about our tablets and about laptops as well, because Google already have its Chromebook, if I pronounce it correctly. So and we still have a significant number of vulnerabilities in software and in huge base of reusable code. So it's all code which written in C.
We are back with our Ranchoddas webcast series this month.
Hello. Hello. Can you hear me?
Setlonet is working. You can carry.
Okay. Okay. I'm sorry. Just a second then. So again, I stopped on a huge number of vulnerabilities. And as we see each and every time, memory corruption is still here. Every time I came with this work and tell to people about the work we're doing, everybody asking why is it decidable at all? Because, if we look for viruses, for example, there are a plethora of different ways to write viruses, and it's probably really hard to predict how virus will be acting and to predict its behavior. So is it decidable at all? But with shellcodes, we have strict structure limitations, and we have size limitation as well. For example, for shellcodes which exploiting buffer and stack corruption vulnerabilities, so we have to have some strict structure, as it's shown in the current slide. So we have activator, which is basically some kind of knobslet. Knobslet is the set of instructions which actually do nothing but increase in program counter. So why do we need it? Because we don't know, when we are an attacker, we typically don't know strict environment of attacking machine. So when we jumped, so our goal is to jump somewhere inside our activator, somewhere inside knobslet. So if we inside it, we just increase in program counter and we got to our decryptor and to our payload and so on. So alternatively, we can have some kind of get PC code. It's some code which tries to calculate its own address in memory location of the process. So typically, as we don't want to have one single item of shellcode, and we want to reuse it somehow. So typically we have decryptor routine. So we want to encrypt our shellcode. We want to have some obfuscation on it. So decryptor routine is typically presented in shellcodes. So actually we have our malicious payload inside it and return address zone. Again, we trying to overwrite our stack in this case. So we're trying to overwrite return address, which points to some instruction after, which point to address to which we have to return our control after the execution of vulnerable function, for example. So we want to overwrite it with the address of our knobslet or get PC code, or to transfer control flow to some controllable memory. Well, okay. So the other issue. So we all know that there exists a huge amount of stack protection, for example, techniques, which trying to prevent stack execution and so on. So, for example, we can have stack canaries. It's just calculation of some pseudo-random number which is stored somewhere outside of our stack. And when we finish and when we return back from our vulnerable function, let's say. So we're just comparing these two pseudo-random numbers. If they're mismatching, we probably want to terminate our process because there is high probability that our stack was overwritten. So it's also protection of exception handlers. It's also techniques for making stack non-executable, and it's also address randomization. So, but unfortunately, all of these techniques can be bypassed by some skilled malicious guy. So it's tricky, but it's possible. Well, and what's wrong with ARM? So we know that shellcodes are here for, as I remember everything correctly, first attack was published in 1996. So they are existing for almost 20 years, yes. So and why we still working with them? For example, for x86 platform, we have a plethora of shellcode detection algorithms, shellcode detection methods, which works sometimes okay, sometimes they have a lot of false positives and so on, but they exist. As for ARM platform, so we have such situations that we already have shellcodes. So we have them in public repositories, public databases already, such as exploitable and so on, and Metasploit databases. But we don't have any detection algorithms for ARM for now. At least such algorithms that will work a little bit smarter than just simple signature-based detectors. Well, so what's next? Again, as I said before, we do this work already for 4 years, and we have a lot of, we have several algorithms and several detectors methods which we did and which other researchers did for x86 platform. So the first question when you're trying to work with a different platform is, are all of those methods reusable? So can we use all of this knowledge base we have already? So, and the first question is to understand how two different platforms can be, how two platforms differ from each other. I mean that, of course, and x86 and ARM platform differs hugely from each other, but which issues can impact how shellcodes will look like and how it will behave in different ways. So we will be focusing strictly on those differences. So let's briefly discuss it. Well, the main difference on two platforms is are the following. So first of all, it's that in ARM platform, command size is fixed. So in x86, the size of each and every instructions varies from 1 byte to 16. In ARM, we have just 4 bytes for each and every instruction for one CPU mode and 2 bytes for other CPU mode. So it's first of all, because like you know how it could possibly impact shellcodes detectors and shellcodes themselves. So actually in x86 we have such issue as self-synchronizing disassembly. It doesn't matter from each byte of set we will start our disassembling. So we will have some point in which we can find our shellcodes. We will drop in some instruction of shellcodes. In ARM, it's not the same. So, and the main difference that in x86 platform, it's easier to detect the presence of shellcode because we will find this instruction, but it's really easy to miss some significant instruction. So there are possible that we will not understand that we're dealing with some malicious code. Well, as I briefly said before, we have two different CPU modes. It's ARM CPU mode and Thumb CPU mode. First of them stands for 32-bit instruction, and second stand for 60-bit instruction. So, and ARM platform provides the possibility for dynamically switching between them. So, briefly describing it, why it's usable. First of all, well, actually, historically, that feature were used for compactization in some, like, embedded systems. In shellcodes, it certainly will have impact on shellcode size. So if you are restricted in the size of memory you want to override, so you can have much more instruction in the same memory with switching between two modes. And it's also the great possibility for obfuscation, because if you have some signature for ARM mode, for example, you can reuse the same item of shellcode. You can switch between two different CPU modes, and it will be disassembling in totally different instruction set. But from dynamic point of view, it will do definitely the same thing. So it's obfuscation technique for ARM shellcode as well. So the other interesting issue in ARM shellcodes and ARM platform is the possibility of conditional instruction execution. So not each and every instruction, but in ARM, but some classes of instruction can be executed or not executed depending on flex values. So and now just imagine totally legitimate program, and you can construct legitimate program and place with flag values in such a way that you will construct your malicious payload from legitimate executable. It's not a rope-like technique, but it's again, it's fun technique for shellcode writers. To be honest, we haven't seen such shellcodes for now, but I believe that it's fun to play with it. So if anybody can do it, go ahead and let me know. It's interesting. Well, the other difference is the possibility of direct access to program counter. In x86, as I said briefly before, we had to have some kind of get PC code to understand at which memory location on which address we are looking right now and where we are to execute our shellcode correctly. So here, unfortunately for shellcode detectors and fortunately for shellcode writers, we have a possibility of direct access to program counter. So we have some specific register which stores program counter, and it's easy to understand where we are. So actually, again, the next difference is load storage architecture. So it's not possible to access memory directly from arithmetic instruction, which we could do in x86 platform. So, and function arguments and return address, not surprisingly, go to registers and not stack. So here is the question how it's exploitable, because, like, for example, typical example of stack overflow vulnerability. But if you have some embedded calls, embedded function calls, so every second and and further calls of instructions goes to stack. So we can gain the control on return address and go ahead. Well, here is a small example of what I'm talking about. So here's example of conditional execution. So in the left column, like here, we have example of the same instruction in assembly language without conditional instruction, and on the right with conditional instruction. So we can see that it's possible to shrink our program, to shrink the size. So it's really good from compactization point of view. Well, here is the example of two different CPU modes. So it's the same example of the same code. We can see that in a thumb mode we have 31 bytes, and ARM mode we have 51 bytes. So actually we have 20 more bytes to go and to add some instruction, to add some functionality in our shellcode if we want to. Well, and local recap. Again, as I noticed shortly before, we did some work for shellcode detection on x86. So how we did it actually? We identified the set of shellcode features for x86 platform, and we implemented detectors of those features. Those features are static and dynamic, so some of them can be detected by static analysis, some of them can be detected only by dynamic analysis. But we wanted to understand, can we apply all of those algorithms to ARM? And we noticed that static analysis is sometimes impossible. Again, for example, in case of this conditional execution, because just imagine, some of popular static analysis techniques for shellcode detection is different analysis on control flow graph and instruction flow graphs and data flow graphs. So when you have a program which consists of instruction, and each and every instruction in this program is conditional executable, so you have a huge number of possibilities for it. It's really difficult to construct this control flow graph, and it won't be really accurate. Those analyses will be impossible. So that's why we have to have something new. Well, okay, I described it briefly already. So the most problem of transferring solutions from x86 platform to ARM platform is conditional execution and one additional CPU mod. Okay, again, the next step in our work, so we already have a set of x86 features. We want to understand other features of ARM-based devices too, and can we identify something new? Okay, here we have the set of features for ARM platform. Most of them were derived actually from x86. It's not Abrahamian list of them, so it's really easy to imagine many more, but it's some certain points. So first of all, it's correct disassembly for a chain of some instruction, because again, shellcode should be executable. So it have to consist of at least some chain of some executable instruction. Again, we are not talking about ROP shellcodes for now. Well, it's a comment of CPU mode switching. I will briefly, I will describe it in detail a little bit later, but here, all of the static features. So let's briefly consider them. So first of all, it's correct disassembly for some chain of instruction. Here is some problem actually, because opcodes of ARM-based instruction have really good coverage. If you will try to disassembly random data, so you will have some instructions, you will have some correct disassembling with high probability. But the problem is that in random data, you will certainly find some incorrect instruction. And when we're talking about, there exists a lot of works which stands that if program executable at all, it should consist of at least several instructions, and if it has malicious behavior, it should complete its instruction chain should exceed some certain threshold. So from my experience, actually, it's not true. When you disassembling again some random data, it's high probability that you will exceed that threshold, for example, from those papers. But actually, when you considering your shellcode surrounded by some random data, you will have just to recalculate this threshold, and it remains true actually again. So it's the very first, the very basic feature for shellcodes. The other one, it's switching between two different CPU modes. So actually, all of examples, I can enlarge it. So all examples I will show here, it's examples of shellcodes which we took from exploitable and Metasploit framework database. Well, it's an example of CPU switching in real shellcode. So it's typical behavior of shellcode. So we have BX instruction, which jump instruction with possibility to switch between different CPU modes, and as all instructions in ARM are aligned for 4 bytes, so we can use the last bit for information about our mode. So the 1 stands for thumb mode, the 0 stands for ARM mode. Well, so we can again switch, and it's the real shellcode. So what we have here. Okay, so it's the other feature. It's the existence of get USPC code. Again, as I said before briefly, so in x86 we were using the presence as feature. We were using the presence of get PC code, which calculates its own location. In ARM-based shellcodes, it's not an issue, so it's not a feature at all, because we have direct access. For PC register, it's R14 actually, but the good feature is when we, if we taken our location, so if we using our register, so if we're taking it, we will have to use it actually. So, and what we see here, so we calculating our location and we're using it. Like we're using it first of all. Well, what we do here? So here in load register in Allery register R14, we will have our program counter address. So it's a decryptor of shellcodes which we took from exploitable. So after that, we use this value for 3 times. First of all, we take next instruction of our encrypted shellcode. After that, we do some modification on them and stores back to memory location. So it's typical example of decryptor. Well, what's next? So the next feature is that again, as shellcode typically have some library calls and system calls, but we try to understand if these calls were initialized correctly. Like in ARM-based, we using 6 registers from R0 to R6. 7 registers actually for parameters. So all of parameters of system calls and library calls goes to those registers, and R7 used for the number of system call. So, and it's exactly what we see here. So we using our system call, so we using information about number of system call, and we have parameters stored. So it's our pattern, it's our simple detector again. So, and on these shellcodes, we see this feature twice. So it's a really good feature, I think. Well, again, as our shellcode is typically encrypted, obfuscated, and so on, we typically see the presence of memory writes and memory reads in some address. So it's load and store cycles. So again, here we have some cycle as well. It's the same shellcode which I described before. Well, and a really simple feature that the return address falls in some certain ranges, and we can understand its ranges, and it's again a really good feature for us. So as for dynamic features, again, all I described before, it was static analysis. Again, we can have more sophisticated features, but why we did it? Because all of these simple heuristics are really good in distinguishes shellcodes, and first of all, distinguishing legitimate random data from executables, and secondly, it's really good in distinguishing shellcodes from some legitimate binaries as well. But each and every feature has a lot of false positives, you know. So we, for that purpose, we combine them in some more complex classifier, and I will describe that later in details again. But there were static features. Here we go with dynamic features of shellcodes. So again, let's briefly discuss them. So first of all, let's read and write to memory. Again, as well, those features we implemented in dynamic analysis. Here we want to understand, do we have decrypted at all or not? So if we read in some like, you know, nearby nearest memory location and writing back to them, so we probably have the presence of decrypt, and probably our considerant data have some obfuscations. So alternatively, we can have so-called non-self-contained shellcodes, which read in instructions, which read in data from its memory location and writes it to some other memory location, like, you know, just to avoid detection of simple detectors. So it's well, really simple feature, but anyway. So what's important in that feature, that in this presence of obfuscation or decrypt and encrypt payload, is that we have to transfer our control flow at least for one time to our just written payload, to our new calculated instruction decrypted payload. So we are trying to understand it as well. Okay, and here is the example of conditional based signatures, like why it's not working. Well, let's consider two examples of the same program with different flex value. So in the left column, so again, depending on flag values, some of the blocks of our program will be executed or will not be executed. So we have, and if some instruction, for example, here in those block at CCS, if it's despite the fact that it's executed in both programs, so if we traverse execution of one of them and the other, so we'll see that we will have different values of flags after the execution. Well, each of those blocks can change flex values, so here we have different results of execution of one single instruction. So again, it's really headache for shellcode detectors. Well, again, as I said it before, so we have those sets of features. For now, for ARM-based shellcodes, it works really well. It distinguishes really well shellcodes from legitimate binaries and random data. But each and every detector, let's say it's vertex in those graph, each and every detector has a huge amount of false positives because they are really simple. But what's good of them, they works really well in such like smart combination of them. On the top of those topologies, we put those detectors of those features which works really fast, but which probably have a huge amount of false positives. But if we're able to, for example, reduce legitimate flow for 80% on the first stage, so we can transfer control of one detector to other more sophisticated detector, let's say for dynamic detectors and other really complex structures. We transfer control for most probable shellcodes. And if we really match shellcodes in our flow, let's say, so it will drop to more sophisticated detectors. If it's possibly just random data or legitimate flow, it will be reduced on the high stages of this topology. So it's a technique for decreasing time complexity and increasing throughput of these detectors. Okay. So again, it's all about machine learning, and this works like decision-making tree. So we implemented such detectors as it's open source tools called Dimorphos. It's based on x86 shellcode detection, but for ARM we have some extension. It's like additional module for this tool. Our experiments, so we have our experiments on 4 different data sets. It's shellcode data sets. We took all existing shellcodes for now for ARM app platform, which we possibly can find in internet right now. It's exploitable, it's Metasploit framework, and other public repositories. So actually, we provide testing on legitimate binaries as well. It's really important because, all of existing, not all of, but most of existing shellcode detection algorithms typically authors don't provide any results on testing on legitimate binaries. But it's the huge possibility for false positives because a lot of control flow graph analysis and data flow graph analysis, it's really like, from that point of view, shellcode sometimes really similar to legitimate program. So it was important for us to have a testing here. Well, we also have tests on just random data and multimedia as well, because on multimedia we also have some problems with existing shellcode detectors. So we wanted to understand how our tool will behave on all of these data sets. So here's results of our experiments. Well, for ARM, again, as we have restricted set of shellcodes, but I can assure you that we tried to provide each and every possible obfuscations here. So we use different decryptors, we use different obfuscation techniques like injection of junk instructions and so on. So despite the fact that real shellcodes, it's I don't remember, but it's less than 100 of them. It's a really small amount, but with all of this, with all of this obfuscation and decryptions and so on, encryptions, I'm sorry, we had for about 2,000 items in this data set. So our tool proves that it's able to detect it's able to detect all shellcode presence for ARM which we have seen for now. As for legitimate binaries, multimedia, and random data, we have those amount of false positives. It's percents, so it's 1 and 1%. It's, well, probably on the big amount on data, it's sensible, but I think it's not a bad result. It's experiment on our throughput. So actually, on shellcodes, it's not really big. Again, because back to our graph, so on shellcodes, we probably will be executing all of these detectors. So on random data, we probably reduce legitimate flow as fast as possible. So that's why we have those dramatic gap between them. But by the way, in x86, it's even smaller. So it's still a problem, and bottleneck actually is disassembler, unsurprisingly. Well, actually, I can show you a little demonstration. So if I figure out how to share it. Okay. Do you see it? So on the right screen, we run our tool called Morpheus in ARM mode, and we're listening for Ethernet 0 interface. So we send an exploit from Metasploit. And we want to look at the red screen right now because we want to understand if our shellcode sent to those interface will be detectable or not by our tool. So it starts working. Yeah, so we can see that we found the presence of shellcode here. Okay. Back to presentation. So, well, nice. It's a question. So actually, I'm done. If you have any question, I'll be happy to answer. So yeah, that's me. Hi. Okay.
Yeah. Thanks, Svetlana. So guys, now we're done with the presentation. If you have any questions, then you can shoot it on our IRC channel, and we'll be forwarding those questions to Svetlana so she can answer it here right now. Yep.
Svetlana,
the question format is already posted on the IRC forum, IRC channel, so you can get the question asking format, and yeah, we'll be sharing those question links to Svetlana.
Well, I see the first question. No, there is no reasons and just examples. It was an example of like, you know, existing shellcode. So it's just an example. Well, any other questions?
Okay, I think if is there any questions, then you can tweet to Svetlana, and she will be online on the Twitter, And Svetlana, thank you for very much for joining us. And it was a very great presentation on your shellcode detection execution techniques. We learned a lot of things from hybrid classifier and decision-making modules. That was the great things. And again, thank you very much. And thank you very much joining for us. I'm Sandeep Kamble, sign out from Garage4Hackers.
And thank you. Thank you for inviting me. It was a pleasure to meet with you guys. So, thanks for a great job.